Guys are always so polite, quiet. Well, welcome back. One more week, 3 more lectures of new stuff. But I got some good news. I've decided you guys have worked you've worked really hard. So, this new stuff, I'm preparing for it last week and this reviewing this weekend. I'm like, oh, I don't know. Let's give them a break. I don't think it would be good to have, the next 4 lectures all just reviewing, and just random do stuff. So I'm going to cover it, but it won't be as deep. We're not going to get into it as in detail, so you don't have as many things you have to worry about. And my real good news, though, is I decided there's a homework on this. I already created it. I'll keep it. It's to your benefit, but it'll be extra credit. So it's still there. You have access to it. It's like all the others on WebAssign. It'll be due Sunday. But it's extra credit. In other words, if you choose not to do it at all, it won't harm you. However, friendly reminder that this material, what we cover, I'll ask a few questions on the final, along with everything else this semester. So it'll probably behoove you to look at the homework. But there you go. Yay. That way, maybe you don't have to stress as much. You've worked hard. You got other classes maybe that would help. So my intent with this was basically I planned the rest of the semester. We got up to this point, and it was like that's how I thought the lectures should be spaced. And it was like, oh, we have 1 week of what? It's like, do I start new material? Or it's not as long as we have on every other thing. So I just chose chapters 22 and 23. It's entitled Electrostatics and Electric Current. So we're going to give you a basic understanding of electricity to go out into the world and notice. And so my hope with this is you'll understand where the sources of charges, what causes them, the forces between them, the fields that accelerate them, how they interact. Since you guys use electricity all the time, some safety cautions, other than don't poke the fork in the outlet. I think you all know that one by now. So that's our intent with this. Questions? Excuse me. All right. Raise a hand. Who's ever shocked themselves? Oh, majority of you. Was it through electrostatics? In other words, somebody gave you a shock, or was it actual current? Do you know? Raise your hand if it was somehow there was something flowing. You were in a circuit or the power or whatever, and it shocked you. Still a lot of you. Well, you're still alive. That's good. Good for you. I think I've only done it once, and it was on accident, and it was actually right here. So it was a power supply. And before they renovated this, I'd been working here many, many years, and you see all these outlets here. Long story short, old power supply that wasn't up to current code, the way it was wired inside. It was all fine, but it wasn't grounded properly. And the outlet, there were a few outlets, that's how I discovered it, weren't grounded at all. So it was plugged into that one, and what happened was when I touched the outside casing of it, that was a conductor, it shocked the heck out of me. That surprised me. Right here, I was cleaning up a demo after one of the classes. I was like, what the? And I went around and tested all these. So fortunately, I reacted fast enough and we were able to take care of it. But what surprises me is that combination had not happened in 20 or 30 years since these things were in that condition. So we were fortunate. Well, chapter 22 on electrostatics then. Electrostatics, fancy word for static charges. Charges that don't move as much. They're not currents. We're not in circuits yet, flowing things. What causes charges? Do you know the source? I bet some of you do already. Say again? What causes charges? What's the source? We say things are charged. What's the root of them? What's creating that charge? Where does it come from? Electrons. There you go. Are electrons what charge? Negative, that's right. Electrons, those are negative. So you can probably guess there's only two types of charges. What's the other one? Positive. And where does it come from? Not the electrons. Protons. Very good. So for those of you that can't remember your basic chemistry, let's look at a hydrogen atom. It's the simplest. It has a nucleus. And then this is the Bohr model of the atom that helps us visualize it, even though it's quantum mechanically not correct. Whatever. You got an electron out here orbiting, not the scale. These are a lot smaller. And in the nucleus, you can have protons. You can also have neutrons. Neutrons. Neutrons are neutral, neutrally charged. They are neither positive nor negative. But the protons are positive, and they're in the nucleus, and the electrons are negative, orbiting around. And for a hydrogen atom, there's just one proton. As you get bigger atoms, you get more of these and more of those. So there's your charges. And I bet you know this too. Let's charge something up. You probably know that you can rub some things together and they get charged. It's not actually the rubbing, or it's not the friction, I should emphasize. I can just go like this. It's when every time materials separate, come apart, it influences these charges because there's forces between them. And so in this effect, it charges these two up. One of these takes more electrons than the other. So I'm going to put this here, and I'm going to do the same thing to it. This, by the way, is a Bakelite hard rubber rod, in case you care. This is animal fur, fake or real, doesn't matter. It's hair. So I've charged these up. This should be charged the same as that one, correct? Do you think it'll attract it or repel it? This is pivotable. It can rotate. So they're the same charge. Oh yeah, repel. Go back the other way. So there you go. Same charges repel. You need to know that. So two positive charges repel. Two negative charges repel. Let's do glass. And this is silk. These two, I'll just tell you, they get charged up similarly, but the glass rod gets charged up oppositely than that one. So I'm not telling you what they are yet, but they're getting charged oppositely. I guess for consistency, let's put that one there and charge another glass rod up. They should be the same, so they should repel also, right? Cross your fingers. There we go. They're repelling. Okay, let's try the rubber rod. Ooh, it attracts it. Come back this side. It attracts. So, there you go. Same charges repel. Like charges repel. Unlike charges attract. So if you had a positive and a positive, they repel. There's forces outward. Negative, negative, they repel. Positive and negative, they attract. And so we're back to forces again between things. Let's do one more before I give you the equation for the force. This one's fun. You can do it at home, show your nephews and nieces. If you pull some tape off, oh look, it got charged. And cats hate this. You can see it attracts to you. So there must be a charge there somehow. Well, let's just put that one there for a moment. Let's pull a second one off. Same thing. See, it's separating from the roll. So it's getting charged. And that one obviously is charged as well. We would think it would get charged the same way as this one. So these are the same charge, right? What do you expect? They do indeed repel each other. But they attract to me. Why do they attract to me? I'm a different charge? Do you think I'm positive or negative? I'm actually neutral. Most of us are neutral. We don't just all around. You got static cling, and it can happen with our clothes, but we're neutral. So a key here is everything's made up of charges. It's from atoms. We're made up of atoms. Protons and electrons. If they're balanced, you have the same number of protons as you have electrons, then there's attracting and repelling going on. The forces are balanced. We say the thing is neutral. It doesn't mean they don't have charges. It just means they don't have more of one than the other. So we wouldn't say they're net positively charged or net negatively charged. That's me. I have protons and electrons in my hand, but they're balanced. So I'm neutral. But let's say this is negative. The tape is negative. What's it going to do to the negatives in my hand? What will it do to the negatives in my hand if the tape is negative? They'll repel. But wait, the tape's attracted. So what's it attracted to? The positives. So this charged piece of tape is influencing the charges in my hand. It's essentially kind of rearranges them. You can think of it as it repels the negatives, and they kind of go away, as however well bound they are, and they get farther away from this charge. Whereas the positives in my hand are attracted and shift a little this way. And so they're attracted. But these two are both negative, and so they repel. Here's a fun thing you can do. Little tip. Loop it over so you can pick it back off the table. Piggyback them together. So they're stuck together. If there's any excess charge, I'll remove it. Let's see. Is it attracted to me? No. So we'd say it's neutral now. They're balanced. But again, if you separate charges, separate the materials, one of these will take more electrons than the other. So one will now have more electrons than it had before, and they came from here, so it'll have less electrons. So one will be more negative and one will be positive. They're oppositely charged, and you can see that they attract. Whoop, they still attract to me.
They love you.
Thank you. That's kind of fun. So how many of you remember your periodic table? Just so you have an idea. General shape, not the scale. But on this side, you have like your hydrogen. There's one, well, the bottom line, even more simply. Over here, if you remember, they have very few electrons in their outer shell. This column will have 1. This column will have 2, 3. Over here, it's full. Their outer shell is full of electrons. It can't have any more. If it does, it creates a new atom. So that's this thing between rubbing things when they separate. Materials that are made out of these things, boy, they're happy being full. And these would sure like to be full. So they will grab the electrons more strongly than this side. If they could just give up a couple, they could go back down an energy level that's full, and that's where they're happy and most stable. And so materials on this side tend to give up electrons and become net positive. These grab them and become net negative. And it's that ionic bond between the ions. Ions are just atoms that are negatively charged or positively charged. And it's this electrostatic force that's holding them together. So when we do this material, the rubber, likes to grab electrons, leaving this net positive. And so these were two negative charges repelling each other. And the glass is positive, in case you cared. Does that make sense?
Which side attracts and electrons again? I missed that part.
Which side attract electrons?
The periodic table.
Oh, this side would like to have more electrons and be complete. This side only has a few, so it's happy to give them up and step back down where it's complete. Its next lowest energy level. Some chemist might cringe, but that's true. And that was the kind of the cause of this. So how many of you rubbed a balloon on your hair, right? Let's do it. Do it now. All right, let's blow it up. I always worry they're going to pop. All right. In theory, this should be mostly neutral. Let's see. A little bit. I got hair here. You can just separate the charges. And the balloon likes, it's latex, rubber, it likes becoming negative. It grabs the electrons. It has an excess of electrons. We say it's negatively charged. The door's neutral. So it's attracting the positive charges in the door, and they're pulled toward a little, reoriented. They're closer to the charges on the balloon, and that's the attraction. It's repelling the electrons in the door. We say the door gets polarized. Polarized. I know, they use the same term with the waves we just had. You can think of it. If you have a balloon that's mostly negative, it doesn't mean it can't have positive charges. It just means there's more negative than positive charges. And you have a door, an object, that has positives and negatives. It will, if this is mostly negative, these negatives will shift. So like this one, it might go this way. They'll reorient themselves. Maybe we got that one. I already had it drawn that way. So they kind of align themselves when we say it's polarized. Kind of like the waves got polarized. That's why they use the same term. So that's how you can attract neutral things. So what is this force? It is Coulomb's law. Coulomb is a scientist's last name. And the force, electrostatic force, I'll put a little E for electrostatic, is a constant. Charge, another charge, and the distance squared between them. Just skip to the chase here. You can probably make sense of this. You got two charges. There's a force between them. We just did that. How strong that force is depends on the amount of charge. If you have more charge, it'll be a bigger force. Makes sense. So if either charge is bigger, you can see the force will get bigger. But you could probably guess too that if the charges got farther apart, they have less influence on each other because they're farther away. That's true as well. That's why the distance between them is in the denominator. It's an inversely proportional. But we do have that squared term, like we had in kinetic energy, 1/2 mv squared. So that meant with kinetic energy, if you tripled the velocity, see a little final review here. If you triple the velocity, what happens to the kinetic energy? It would be 3 squared, which is 9. So the kinetic energy would be 9 times greater. What?
That symbol is K.
K, yeah.
What I mean?
It's a constant. So the force is proportional to the charges and the distance. It's exactly equal. You throw in this constant. That's defined in your book. It writes out the thingy. For this class, the actual value isn't as critical to me. The key point is force is based on this. That's what we're going to deal with. You can solve it exactly. Look that up in your book and solve. So what I was getting at, if you take charges and you move them so that they're twice as far away, what happened to the force? It's 4 times stronger or less strong? Less strong. That's what it means. That's called an inverse square law. In case you want to know what it's called. I bring that up because you might find it interesting. That's how light works with light intensity, sound intensity. Waves fall off on an inverse square law that we didn't get to cover. So like if this is the source, you can see that they go through one square here. But if you double the distance, it now goes through 4 squares. Can you see that? And if you triple the distance, it's 3 squared. There's 9 squares. This kind of can give you a visual of the inverse square law. Even though you're progressing linearly with distance, the intensity of the wave, so it'd be less bright or less loud. And with Coulomb's law, less force. And this is the same law for gravity as well, between 2 masses. You just replace masses here, and it has a different constant. That if the masses were 3 times as far away, the gravitational force between them would be 9 times less. So that's the inverse square law. And that's how charges interact. Now, go back to Newton's third law. If you just have one charge, all by itself, totally isolated, there's no force on it because there's no other charge to influence it. That makes sense. If you just had a proton sitting all by itself, it's neither attracted nor repelled. You need 2. And Newton's third law is for every action there's an equal and opposite reaction. Or as I prefer, all interactions come in pairs. So these forces I drew, these 2 forces are this. You want to find out this force? Plug in that charge and that charge, because this is the one that's pushing it, right? But this is the one that's pushing it. The same charges are involved. They're the same distance away. So this is the same force each positive charge feels. They're equal and opposite. Do you see that? It's Newton's third law again. Same if they were negative. Same if they're attracting. You would plug in this charge and this charge. Those are the 2 involved. They're that far away, so they're being attracted with that much force. Each one, the force on the negative charge and the force on the positive charge. You sure you have that? That trips up a lot of folks. Unless you're sitting there going, yeah, that's duh. Makes sense, Adam. But you look at the homework and things, it seems to trip people up. So that's why I'm emphasizing it over and over here. So that's Coulomb's law. That's our force between all these charges. And that's the electrostatic force that drives all electricity. It's that forces between attraction and repelling that get charges to move, and we can flow and power all of our cool techno devices in this world now, right? Okay?
How much charge would it take to stick a person to a wall?
How much charge would it take to stick a person to a wall? So in theory, we could calculate it. I've never done that. But let's see. If we could, we know this is a constant. The wall, I guess you could approximate the microscopic distance from your charges to those charges. You know your weight, right? You pretty much have to have an equal electrostatic force to balance your weight, to hold you up, let's say. So the charges in the wall, you'd have to approximate. So you start using Avogadro's number and how many atoms and molecules there are in the door and what that charge is. That's probably the hard part, is estimating the charge in the door or the wall and the charges in us. But people have, we could surf the web and get a good estimate of how many molecules do you think make us up, at least on the surface. Anyway, you put in those two charges, well, put in everything else, you could solve how much charge you'd have to have on excess of yourself to have that force to overcome your weight. I would assume it'd have to be a heck of a lot. Because generally, you can tell electrostatic forces aren't extremely strong in our normal everyday world compared to our wonderful weights. But that could be fun. Okay, some other terms here. Yeah, this. I'm going to charge this rod up again. Not yet. I'm going to charge these ping pong balls up. I'm going to rub them. And when they separate from the hair, every time they get charged up, they're the same charge. And you can see that electrostatic force on a macroscopic scale. This one I've done. We did it at the lab at Colorado State University where I used to work. Because the ping pong ball has a certain weight down, right? And these have a force repelling each other out. So you'll have to play components because they're not lined up. You got a force on the ping pong ball that way, and you have gravity going down. It's two forces. You can estimate the electrostatic force off of its weight, what it needs to be, and then work backwards from that. If you know the force, you can figure out how much charge is on that ping pong ball. And from Avogadro's number in chemistry, you can get how many electrons, extra electrons it has. Let's charge the rod up. This is called an electroscope. An electroscope. There's a little needle here that's free to pivot. And so if I transfer the charge on here, your book talks about 2 ways to transfer charge. So that's what I'm going over. This has excess charge. If I just touch it, only the charges right there are free to move to it. Because this is called an insulator. Insulator, you've probably heard the term. That means they don't let charges flow on them. So only the charges that were right there in contact flow. Any excess charge over here didn't go onto there because it can't flow. It can't move readily on the rod, so it's an insulator. So I'm going to kind of drag that charge and let it make direct contact. This is charging by conduction. Conduction. That's direct contact. And you can see some of those excess electrons went onto here. This is a conductor. It's metal. Metals are conductors. The electrons are loosely bound to the atoms, and they're free to move around more than they are in insulators. And so as soon as you put charge on there, they spread out. Why do they spread out? They're free to move, but why would they want to spread out? You have the answer. The metal's a conductor, so that allows them to spread out, but why do they spread out? I'm taking excess negative charge, and I'm putting that negative charge on here. It's trying to equalize. Because do negative charges like each other? No, they repel. So they repel and try to get as far away from each other as they can on the conductor. So that's why they spread out. The fact that it's a conductor just lets it. So that's how you can see it repel. Can you guys see that okay? Gives you an idea how much charge is on there. If I touch it, I'm neutral. That has excess electrons right now. I touch it. Those excess electrons found a path through me to ground, where there's a big reservoir. It became neutral again. So I'm a conductor. We just saw that. I'm not as good a conductor as metal, but that's how you guys got shocked. Let's charge it back up. All right, here's metal. This should work, right? Discharge. So that's a conductor. Charge it back up through conduction. Plastic, what do you think? Seems to be insulating. It can't flow through it. How about wood? Insulator?
Nothing. Yeah.
Somewhere in between. So it's a pretty good insulator, but you can see it must be conducting something. And this varies on the wood. The type of wood, how dry it is, because moisture is conductive, water.
And your hand doesn't change anything there?
My hand?
Your hand doesn't have to do anything?
If I just set it there, it could move to the wood, but it could probably stop, fill up the wood, and then be repelling. I'm giving those excess, if it can move through the wood, it can move to me, and we saw I'll finish it off. So see, it's not changing now, but if I touch it, we could go a little further. So wood is often used to insulate things, and it's a pretty good insulator, but it's not perfect.
I used to have a piece of wood next to my stove because it was electric, and for some reason, the only one who got shocked, and that was me, not nobody else.
Also, you insulated yourself from the stove with wood?
And yeah, we put a piece of wood.
Yeah. Wood usually insulates well. It varies. It depends on the size of the voltage, which we're going to learn about, but I'm sure you've heard the term. How much current's actually flowing, the humidity, how greasy, wet, dry this is. So wood isn't a guarantee you're protected, is what I'm getting at. Let's watch this. This is charged. If I bring it near the metal, I'm charging the metal. I've polarized the charges in the middle, right? It's neutral, just like my finger was in the door. And so I'm polarizing. If this is negative, I'm bringing the negatives away, repelling them, and the positives are attracted. So while this is polarized, watch. I'm a path to ground. I'm going to touch the bottom here. Oh, I took charges away. Now let me remove the rod, and it remains charged. I've never physically touched it with the actual charged rod. This is called charging by induction. Not direct contact. I've induced, polarized those charges. They kind of turned and rotated like this. If I touch one side, let's do it again. This was negative, net negative, brought it near. The negatives got pushed away, the positives attracted. If I ground it, I'm allowing those negative charges to escape. Then I remove it. What's it left with? Less negative charges. So it's now positively charged, because I've removed some of the charges off of it. But I've charged this up oppositely than I do with conduction. Conduction, it transfers it directly and it becomes the same charge. With induction, I never actually touched it, but I removed some charge so that it became the opposite charge. Let's see if we can see that. This should be positively charged. So if I bring a negative rod near it, it should attract, right? They're opposite. You can see it attract. Let's try the glass. This glass is positive. That's positive, so they ought to repel. Yes, it gets further away. It's repelling. So it did indeed get charged oppositely than it did by this one. You following me? Say that again?
The glass does a better job with that.
The glass does a better job? This will work either direction. I could have charged it first with this. You can charge something by conduction and induction using positive or negative. So there's our term. We got conductors and insulators, whether it flows or not. Attraction and repulsion, Coulomb's law, charging by conduction and induction, direct contact or not. Things get polarized, still polarized. Okay, the electric field. This one can seem foreign to folks. So my analogy is, you're used to fields. We just usually don't call it a field. Gravity. And we've studied that. So that's going to be my analogy, a lot of the gravity stuff we did. See, it's a way to review, too. We're in a gravitational field. Our mass is in it. And so what does that field do to us? We called it, it causes us to accelerate. We had that formula. Newton's second law. Force equals mass times acceleration. If you accelerate a mass, it means a force was applied. In order to accelerate it, you got to exert a force. You exert a force on something, it causes it to change its velocity, its motion. Acceleration is a change in velocity. You can write that this way. Same idea, that if you have a force on a mass, it's going to accelerate. That's our guide to thinking. Bigger force accelerates more. More mass accelerates less. That's inertia, Newton's first law. It's going to resist that change more because it has more inertia. So with electric fields, these charges are going to be like the masses, and instead of being in a gravitational field and getting accelerated, they're going to be in electric fields and accelerate. Oh, did I? Nope, not yet. So, here's the analogy. The electric field is a force on that charge. Or you can rewrite it so it matches this. You're going to take a charge, and it's like accelerating it. You put it in that field, and it'll move. It feels a force and accelerates. I like looking at it this way, and when I forget this equation, which I still do, this is exactly how I remember it, this analogy. So when this stuff starts getting confusing to you, just try to relate it back to gravity, and maybe it'll make more sense. All right, let's look at some of these electric fields. If you have a positive charge, we draw electric field lines to help represent this field because it's more foreign to us. From a positive charge, the field is going away. They go away from positive charges in all directions. So that represents the electric field lines. So we can visualize what it would look like around a charge. Negatives come towards it. So if you had a positive and a negative, they both have their own electric field. But what happens in the middle? Well, it's got to go away from this one, and it comes towards these. So the one right between them looks just like this. Over here, it goes away. Over here, it's coming at it. And maybe one up here, it doesn't go straight at it. It starts heading away from the positive, but it goes towards the negative. And you'll get lines like this. So these are going away on this side, and they come in at this side. Does that make sense? You can get all kinds of funky configurations. Here's my tip. You figure out the direction of electric field lines by pretending you have a positive test charge. Let's see which way it goes. Take a positive test charge and just stick it somewhere. Let's say we put it right here. A little test charge. Well, what's the interaction between these two? They repel. So you know the force on it right there is away due to the positive charge, correct? That's the Coulomb's force. Now let's look at that test charge from the negative. What's the interaction between these two? They attract. So there's a force over here. Which of those forces will be larger? What do you think? From where I drew it. Let's say this is the same amount of charge as this one. They're just opposite sign. Which one of those forces should be larger? The one in the middle? You mean that one? Or that? This charge. We're still on it for now. So if this feels a force due to this, it also feels a force due to this. So this test charge feels two forces. Which of those forces that it feels should be larger? The amount of charge is the same. So if you look at Coulomb's law, we're not really changing the Q values. What are we changing though? The distance. Which one's it farther away from? The negative. So I'd expect that force to be smaller. So if we drew it more accurately, this would be bigger, and this would be smaller. There's our two components. A little, parallelogram thing, and it heads that way. So right at this point, it's trying to go that way. And that's how we've drawn it. Do an easier one. How about right here? It feels a force from this guy that way. And it feels a force from this guy that way. You add them together, there's a force that way. That's the way it's going. And over here, from here it feels one that way, right? From here it's attracted. If it's the same distance, those should be about the same. And so right at this point, it's headed that way. Right at that point. When it gets over here, it rotates a little. So that's how you could test yourself with these. Take a little test positive charge, and you can always see which way the electric field lines are going, which way the direction of this force would be. So if you had some parallel plates, let's say two plates that are charged up, one positive and one negative. What do you think the field lines would look like in between the plates? They go away from positives, and they go towards negatives. So, they're all headed like that. You can make a nice little uniform electric field in between the plates. When you get to the edge, some of them are going to fly out this way, right? But it might get curved around and come back. You'll get things like this. Ones will come in on this side. They go everywhere. And you'll have ones going away. You might have one that, whoo, it comes back. Another nice thing about electric field lines is they help us visualize how strong the electric field is. For example, here's the electric field. Where do you think it's strongest? Point A, point B, point C. What do you think? Your gut's probably right. B. Why? Do you have can you? It's closest. That distance again. It's closer, so it feels a greater force. Look at the field lines around here. At that same distance away. The field lines are closer together. When you get out here, see how far they're spread apart? That's an indicator. That's why scientists like electric field lines. They can help you visualize the strength of these fields and forces. So skip to this one. Where's the field the strongest here? Well, you just go, where's the electric field lines closer together? Right around them. And in between, they get squished together more than out here, right? And here they're spread out a lot, spread out a lot. So the field will be stronger between them than it would be out here in the perimeters, which I bet makes sense. And same here, the field's the strongest in there, where they're closest together, not out here where they spread apart. Let's shield some. This is kind of fun. This is a toy. I intend to explain how it works more next time when we use this. Has anybody seen one of these? Recognize it? Maybe your high school teachers. It's a Van de Graaff generator. This is a toy Van de Graaff generator they created. They're awesome. Fun fly stick. We'll go over that next time. Basically it's battery powered, and it charges up this section internally. Here's some conductive mesh with some thread hanging onto it. So I'm going to charge this up, touch this. Since it's a conductive metal, charge should transfer onto the screen. Come on, baby. It's working slowly. Can you see what's starting to happen? These threads can kind of help you visualize the field lines. This gets charged up negatively. Wait, is that right? No, positively. Positively. So there's positive charge going on to the wire mesh. The positive charge transfers to the thread, and they repel them. They try to get far away, right? We can see it. It's like an electroscope. We can tell there's charge on there. But can you tell where the charge is at? Is it everywhere? I can see it repelling out here. But can you see on the inside? The threads aren't moving. They're still straight down. You can shield electric fields. Two cool things. If you have a conductor and it's hollow so you can get inside, it shields the electric field from being inside. It's kind of like, let me draw a picture. I got time. Let's say you had a big conducting sphere. It went all the way around. Here's the center. Let's say you're here at point P. And so that point is influenced by charge on the sphere. And it's all of it. But, so we can handle it. Let's just pick some here. Let's say if we had some there and some there. Let's just say this point is influenced by this charge over here. We'll call that area B. And this charge over here, area A. You know, it'll be a circle. Which one will give a bigger force at point P? Right? This charge, if you were here, you'd be influenced by this charge and this charge. Who wins? What's your gut say? B. Why? It's closer. Good. Because it's closer, B does influence P more. Yes. But there's something else going on here. A has a lot more charge. The area that's affecting point P is more area, so there's more charge, there's more Q. And area goes by a factor of square. The circle, it's pi r squared. The bottom line is here, they both influence it. Because B, it's closer to B, that makes it stronger. But because there's more charge influencing it here, that makes it stronger. And they actually completely balance each other out. Bottom line, at point B, there's no electric field there. They would feel no net force due to these charges. And that works for any point inside a conducting sphere. The idea is you can shield things inside so they don't feel an influence from this electric field. That's what's happening to the threads here. If I separate these, some of them, yeah, it's not as obvious. Let's just do this on an end. So we talked about electromagnetic waves. They're coming in, right? What's an electromagnetic wave? An oscillating electric field and magnetic field. So there's an electric field. It causes the charges in here to start moving. They have to hit the antenna. And then this can convert to sound. Conducting cage. It's shielding it from the electric field. They can't influence the charges in the antenna. You guys have seen this. You lose phone reception. You go in an elevator. You're being shielded. I'm the antenna.
It's a boatload of Salt Lake's greatest.
I'm picking up the electromagnetic electric fields. Have a nice day. Whoop. This is brass. But any metal conductor.